Hello, everybody. We have started the stream. We'll make sure the stream is in fact streaming. Oh, that looks like a good sign. The stream is nice. All right, haven't made that mistake in a long time, but we will continue to check every time because thought of talking to myself for an hour and it not at least being recorded sounds terrible. All right. I will be taking questions regarding the assembly crash course module. I'm willing, or not saying willing, we're going to answer your questions here. So if you have any questions in particular about x86-64 assembly that relates to the module, I'm happy to answer those questions throughout this office hours. I will not be going over any of the levels in particular, but if you have a well-formed question asking about a concept that gets explored in one of these levels, that's totally fine. You're just going to have to articulate the question of what you're confused about, and I can demonstrate whatever that concept is. Okay. Let's make sure that there are some number of people, it looks like. Cool. Giving people time to join in. If there is questions about x86-64, now is the time. In the meantime, while we're waiting to take some questions, we'll go ahead and demo some things related to it. Cool. Okay, so we're just starting up a random challenge so that we have an environment to play in. Hopefully that started. This thing. Well, what's going on here? Not a good sign. What's going on? Why is the site not working? What's happening? There we go. Fine. Not sure what that's all about, but hopefully we are good to go now. Okay, and so as a reminder, this assignment is due very soon. 2 days, 12 hours, 54 minutes. Highly encourage you to be done with this module well before the due date. As in, like, be done with it tomorrow. That way you don't have to deal with any potential disaster of the server being slow near the end. Make your life a lot easier if you just pretend that it's due tomorrow. Okay. So we, in this demo, are going to write some C, and we're going to analyze what the heck's going on with the assembly of that C. So as we've talked about in the class, GCC, the program used to compile this, right? So we have this program here. It's got a main function, it has a foo function, and it passes some arguments to foo, which really this is just the add function. We've seen, and let's do this, ps1 equals that, cd live, cd assembly, and we'll rm core, rm3, rm test.bin, oops. Good enough. Okay, and we'll remove test and test.o. If we go ahead now and GCC this program, so GCC test.c, and we produce test_c, We have just converted this C program, so literally this text here, and we have produced a bunch of assembly. So if we look at this program using objdump, and we jump off to main, we're going to see a whole bunch of assembly instructions. Now, I haven't explained some of these instructions. For example, this NBR64 instruction, we haven't worked with. We actually haven't worked with the leave instruction, which commonly appears before the ret instruction. But you probably recognize a lot of this. So for example, push RBP, we're pushing RBP to the stack. We're moving RSP into RBP, so we're setting RBP equal to whatever the heck RSP is. We're subtracting hex 18 from RSP. These are all operations that should make sense to you. We throw EDI or RDI, whatever you want to think about it as, into RBP minus hex 4. RSI goes into RBP minus hex 10. RDX goes into RBP minus hex 18. We're just putting these registers into memory, right? It's not that interesting necessarily. We're just saving this to memory. Then we put hex 44 into RSI, hex 17 into RDI, and we call foo. What does foo do? Well, it pushes something onto the stack. You'll see very common at the beginning of a function. We're going to push stuff to the stack. We're saving whatever the heck this RBP register is. We're saving it on the stack. Moving RSP into RBP. Now, it's probably pretty clear why we save this on the stack, because guess what? We're about to just overwrite it with RSP. And then similarly, we put stuff into memory, put stuff into memory. And then this is not very efficient code. We really didn't need to do all of this nonsense here of putting it into memory and then pulling it back out of memory. But the basic gist of the compiler, at least without optimizations, is not necessarily intelligent. It's just following a pattern. It says, hey, this is some local variable. It's an argument specifically, but it's a local variable to my function. And local variables go on the stack. It goes into memory. So guess what? They got passed in through registers, but this is the location of this local variable specifically refers to some memory location. And so even though we don't really need to be so tight with our registers by just saving them like this, right? We could have just moved EDI straight into EDX if we wanted to. Really, we didn't even need to do that, right? We could have just added EDI and ESI, right? This add instruction, we could get rid of all of this and just do add EDI and ESI and call it a day, right? We didn't even need to do any of this either, right? All this function really needed to do was add EDI, ESI, and ret, right? It could have been 2 instructions, but the compiler is just following a pattern. It's got a set of rules and it's running with those rules. And that's how we're able to do more complicated programs. And it just formulaically produces this assembly. You could actually write some sort of basic compiler if you wanted to. You could imagine defining the rules of when we have these local variables that, hey, we just need to declare some space on the stack for those local variables. We need to remember where that space is. On function call, put that into memory. If you start creating other local variables, right, we can have int a equals 42, and we'd need to make sure we reserve some space on the stack for this a variable, and just never associate a local variable with a register. Always associate it with a place in memory. And then when you need to actually do something with it, so for example, if we wanted to then also do plus a or something, then you pull it out of memory, put it into a register to be able to temporarily use that value. But just always stick to memory, follow this formulaic pattern, and you're going to be good to go with your local variables. And that's what GCC is doing here. And I'm curious actually, so there's a way to compile it with optimizations. I guess we can look at the man page. O3, I thought it was O3. I think O3 is some good optimizers that were really optimized. Yeah, see, O3, optimize yet more. O3 turns on all optimizations. So we've got we're if you think about it, right, a lot of people are writing their programs in C as opposed to assembly. Now, of course, we all know C is becoming, maybe less popular than, the cool modern languages like Rust or whatever, or, C++, a little less modern, but maybe you consider that an iteration on C. But nevertheless, it's much more common to write your program in a higher level language that gets compiled down. And you want these programs that you write to actually be a lot more efficient. You don't want to be moving things into memory just to pull it out of memory if you don't have to. And so that's why we have stuff like optimizers. So normally if you're running, let's say, Google Chrome, uh, or Firefox or whatever, popular massive program, Linux, um, it's written in a language like C, and it's compiled efficiently. Or not necessarily efficiently, it's compiled optimized. So I'm going to see what the heck happens to our code if we add in a -03. I'm not sure how it's going to feel about this. Let's see. So if I do objump now, so we added in this 03 flag. If I go to foo, yeah, look at this. So this is not what I said I would do, but this is certainly more optimized. Well, I guess we added in that add a. We didn't have that before. Let's go ahead and get rid of that. So we see that it managed to produce something smaller, even still doing that though. But we'll remove that for the moment, and we'll see it has. So I guess I'll point out here real quick. NBR64 for our purposes right now in this course is a no-op. It does nothing. In reality, it is a security mechanism that we'll talk about kind of later on in this course. This actually is specifically a security-related instruction. But for our purposes, we can pretend that it does nothing. So just kind of ignore this. And then this nop is just adding spacing to the program. Again, we can ignore this. So all we have are these two instructions. Now we know the ret instruction. It's going to get us out of foo. We haven't really talked yet about the LEA instruction. I think I pointed it out last week in one of the lectures. The LEA instruction is kind of interesting. It means load effective address, and it does this addressing mechanism, this addressing scheme where we use these square brackets, right? We've seen this with move, for example, when we want to move something out of memory, right? We can almost imagine instead of LEA, this was move. And we would be accessing somewhere in memory. And this is also kind of a more complicated memory accessing scheme than we saw last week. Last week, we were specifically doing something like just RDI in these brackets. As we see here, you can do kind of more complicated memory accessing schemes. So for example, you can add two registers together mid memory access. So this literally means what you might be expecting. It means do RDI plus RSI and RSI times 1. Technically, this RSI could be times like any constant value, or at least any, I don't know if it's a 8-bit constant value or if it can get up to a 16-bit or 32-bit. I'm not sure what the restrictions are for this multiply portion, but this is actually the full version of memory accessing. You can always do register plus register times constant. Now, we've only ever just done, maybe treat this as instead of times 1 times 0, like just a single register. But memory accessing lets you do kind of like some addition and multiplication in here. And the reason the architecture supports this, you might say, why do we need to support this? Why not just do your add in a previous instruction, right? We could have we had RDI in a previous instruction, we could have done add RDI, RSI. And if you needed RSI times something, you could have done mul RSI times 1 or times 7 or whatever you wanted to do. And the reason for that is x86-64 is it allows you to do these more complicated operations. It's a complex architecture. So it's not like a RISC architecture, right? Where RISC meaning reduced instruction set. It allows these real extra instructions, right? It kind of does a lot in one. Anyway, so that's what's going on here inside the square brackets. You could do the same thing with move. You could do this complex thing, this addressing mode inside of a move instruction. What the LEA instruction does instead, though, is it allows you to use this add notation with a multiply in here, right? This complex expression within the square brackets. But it actually, even though you see these square brackets, the purpose of this is not to pull out of memory. This instruction does not pull anything out of memory. Instead, it's kind of setting up a pointer. It's setting up a location in memory that maybe you would later then move out of, right? Then maybe later we move out of EAX into something and you pull out of memory at that point. The LEA instruction allows us to use this notation here, the square bracket notation, except it may be a simple way to think about it is the square bracket part just doesn't happen. We don't pull out of memory. So that's what LEA does. It's load effective address. It loads the address. It does all of the addressing stuff, but it doesn't actually go into memory and pull it out. And so we have this optimized code here that is abusing the fact that we can do addition and load it into a single instruction. And this allows us to just write more efficient code. This is an optimization. Again, this is this incredibly optimized code. And if you think about it, like why not just do the add instruction, for example? Why not just do add RDI, comma, RSI? Well, the reason we don't do that, this is slightly more optimal, is that if we did add RDI, comma, RSI, we would then also have to move RDI into RAX and then ret. Because remember, the return value has to be in RAX. And so add doesn't allow you to store into some destination register, right? You only get to specify 2 registers. You don't get to specify 3 registers. But by abusing the load effective address instruction in this way, we get what we want. We get to add 2 registers together and put it into a different register. And all of this only takes 3 bytes worth of instructions. So it's just more optimal. So that's why it's a little more complicated. And then we ret. I guess if we look at main, you can see if that looks different. Yeah, it actually does. What's going on here? Oh, this is very optimized. Is this doing what I think it's doing? Yeah. This is actually pretty funny. Main is just immediately returning. It's not even calling foo. So here we wrote foo hex 17, hex 44, and then we return. In assembly land, it doesn't even call it. And again, this is because it's optimized code. The compiler was able to analyze that there are no side effects from this function, as in we don't modify global memory in any way. It's just totally local. We take 2 local arguments and then we return something. We don't do like int x equals 42 and do like x equals arg2 or something with like a global effect. It's entirely local, and we don't save the result. So the compiler is able to say, okay, well, that's cool that you wrote this program that's going to go and call foo, but this is a waste of our time. This will do the same thing, and it's just more efficient. Just don't call it. So it actually just completely optimized the call out. Now I wonder if we do int x equals foo, I'm wondering if it's going to optimize it out. It might still optimize it out because nothing depends on x in a way that matters. So let's see. Let's see what happens there. Yeah, see, same thing. It doesn't care. Now if we return x, right? So main returns x. Now we're going to need to do this call for sure, because calling this is crucial to getting the correct return value from main. Let's go ahead and look at that. Yeah. All right. This is what happens when we use O3. It still doesn't mess around. The compiler is very smart if you let it be. And then, I mean, I say that, it's also still very dumb sometimes, but it has some very smart things to it. It says, why would I even bother calling this? We're adding a constant with a constant. It's able to like follow through into this and see what the effect is going to be. It says you're going to be doing add. You're basically just going to be, or let me say this. This is the equivalent of this with substituting these values in, right? Which is the same thing as not doing the addition, right? We can determine all of this at compile time. We don't need to save this anywhere. Just return it. Don't mess around. Just return it. It's the same thing, right? And so that's why we literally just move the result into RAX, call it a day, return. Okay, again, this is optimized code. In some ways, I think looking at optimized code is easier because, especially if we're doing these very, very basic things, unoptimized code, as we saw at the very beginning, is constantly moving in and out of memory, and it's kind of just feels a little tedious and feels a little verbose because it is. It's just very formulaic, no optimizations applied. Whereas once we apply the optimizations, we don't do these unnecessary things. There's less to read. It's in some ways a little bit easier. Of course, then we have to like see kind of crazy things like this. This actually isn't that crazy of a thing to do. This is very common to see this notation used like this, even though we're not doing any memory address, right? RDI and RSI actually aren't ever, like this EAX thing is never going to be dereferenced. If it was, it would segfault. But even still, the CPU doesn't care that this isn't actually addressable memory. We can still use this instruction, even though it's kind of morally intended to be doing addressing related things. We don't need to do that. Okay, so that hopefully clears some of that up. Oh, your image is blocking the code. Well, that's a disaster. Oh, it's probably... Huh. Hold on, let me see. Let me pull up the stream and see. Well, that's unfortunate. Well, it's only quasi-blocking. I don't think we missed anything too bad. But I see the issue. Yeah. We're getting close. I gotta remember this corner is dangerous. Dangerous corner right there. See if I do this, just in case anyone was worried. This right here. All right, so we're doing this. Okay, so I still don't see any questions in chat. So if anyone has any questions specifically related to assembly, right? Anything like, I don't understand memory, I don't understand what the heck are these small versions of registers, whatever you don't understand, it's totally okay, right? This is the whole point of this, is to explain these concepts. I will not be going specifically into any of the challenges, but concepts from a challenge, totally cool. Just make sure you don't say like, oh, help me with level 7. Explain your question. Why does the LEA have A plus B times C? Okay, this is a very good question. So why, I guess there's kind of a number of ways of thinking about that question. So we have the ability to do something like this. I'm just gonna put it into C land. We have the ability to write an instruction that looks something like this. So the question is why? The depth 0 answer to that question is because the architecture says so. The architecture allows for doing this, and so maybe we can just say that's why. In some cases, the truth behind why something exists gets very like, I don't know, at some meeting of minds at an Intel headquarters, they determined that lots of programs do this operation, and we decided that we need a more complicated instruction that encapsulates that for optimization purposes. We realized that we can reduce program performance, or we can improve program performance by 3% because our architecture supports this complex instruction. And so it's such a common thing, let's go ahead and add it. And now everyone just gets a 3% optimization on their program because compilers can emit an instruction that looks like this, right? This is how some instructions presumably come into existence. Now, looking beyond that kind of unsatisfying answer, or maybe going a little deeper on that, why is this so important? Why did people declare that at some meeting somewhere in a committee determining what the architecture would look like? It has to do with pointer operations. So pointer operations are very, very, very common in C. So for example, what do I mean by that? If I have some character array, or maybe we won't worry about characters. Let's say integers. Integers are easier to reason about. Characters are scary, right? It's like character. Really, it should be a byte, and then it would be, but whatever. Int A, and we'll say we've got, let's think about how, let's make sure we don't incorrectly write this. Int A sub 8 equals, can I just do this? I don't even write C, so we gotta be careful here. Let's see if this will compile for us. 2, 3, 4, 5, 6, 7, 8. And I think that's valid syntax. We're gonna find out. Hopefully you know what I'm trying to do. I'm trying to define an array of 8 things, 1, 2, 3, 4, 5, 6, 7, 8. And let's write the max function, which takes an int pointer, we'll call it array. And what we're going to do, and then, well, we have 2 choices here. I think I talked about this last week in class. We have the option of passing around just one thing that's like null terminated, or passing around a thing that just is a thing, and then also passing around the size, right? We kind of have 2 options. We'll go ahead and use the size variety, since last week we're looking at C strings where we take like the null terminated variety. And it doesn't have to be null terminated. You could like terminate with hex FF. It's just now you can't use hex FF for anything except termination. But in this case, let's go ahead and do size. And what we'll do is we're going to write the program, and we'll say int max equals 0. We're going to kind of assume that we're only talking about positive integers here. Maybe we'll make that crystal clear. We'll say it's unsigned integer array. Unsigned int. Extra crystal clear. And we'll say for int I equals 0, I less than size I plus plus. Hopefully you've written this sort of thing before, right? We're just getting ready to go over this array. Hopefully you see where we're going. And we're going to say if array sub I is greater than max, and we'll say max equals array sub I. Now, maybe this code looks kind of not great, whatever. It does what we are expecting it to do, right? We're finding the max value. Actually, I'm a little bit scared of name clashes. I don't write enough C to know what the heck happens with a name clash here. So we're just going to call this thing result. Okay, and then let's say we write the program, or let's say we do return max A size of A. We'll make sure, we'll confirm that we didn't make any mistakes here. And remember, we're trying to understand this LEA a little bit better. Cool. All right, let's compile this. So GCC, we'll use O3 unless we determine that O3 makes it more complicated. Unclear whether O3 is going to be simpler to read or no optimization is going to be simpler to read. We'll start with this. Let's look at main. Oh boy. I'm seeing something that's telling me that we are not liking this. We're about to be doing some very optimized stuff that has to do with the XMM registers, but it should allow us to do more than 64 bits at a time. This is going to actually allow us, I don't even know, XMM, well, how many bits is XMM in x86 64? So I said that 64 bits is the max. That was kind of a little bit of a lie. XMM registers are 128 bits. It allows us to like do lots of things at once. Basically, allows us to do parallel processing. We're going to get rid of that. This is not going to be happening because this is not going to be worth explaining. Let's see if O2 doesn't do that. Okay, I think well, it inlined this, so we're not necessarily liking that either. Let's try O1. Inlined it, meaning it just said, screw this function call. We don't need to do a call. Just put what's going to happen just straight into main. Like basically copy and paste the code of main straight in. Looks like this inlined it as well. And so we are leaving the optimized world so that we can understand what the heck's going on here. Wait, what? Oh, wait, that might not be true. I see it setting up an array. It might not have been inlining. Okay, it looks like that is inlining. Call max. Okay, cool. All right, this is what we're going to be rolling with. This version of the assembly. So we're just going to kind of try and jump straight ahead to where we're initializing this array. So we see right here, we've got this statement here that needs to be executed. Somehow we need to set up this A thing. If we look at this, right here, it decides to move 1 into RSP, 2 into RSP plus 4, 3 into RSP plus 8, 4 into RSP plus C, 5 into RSP plus 16, or hex 10, etc., etc., etc. This is initializing this thing right here on the stack. And it crucially has to do this initialization in this way because that's just what it has to do. If we wanted this not to be like done through instructions, you might be saying like, why not just like store these bytes next to each other? We could actually do that by making this a global variable. And then these bytes, these raw bytes sitting next to each other, they'll just be in the ELF. And we don't need to do this initialization like this. So we'll observe that real quick. Okay. And now we don't do all of that initialization. Instead, we do this crazy LEA thing again. Like I said, LEA, very common, as we'll see, especially once we start getting into the reverse engineering module, but we're kind of doing that to some extent. It's taking RIP plus this crazy offset. So remember, the compiler is generating code. As long as the compiler generates code that is correct, we're good to go. It turns out, so RIP being this instruction, this address right here, pointing to the next address, turns out that RIP plus this offset just points further into memory, past the instructions, and into just saved data. So if we look at, we look at this address right here, so we kind of want to look at new terminal, Python. We want to look at like this plus this, 4020. So if we look at 4020 in this obj dump, we're going to see that we have 0, 1, 0, 0, 0, 0, 0, 0. So this is 1 stored as a little endian 32-bit integer, 2 stored as a little endian 32-bit integer, 3, 4, 5, 6, 7, 8, right? So it's literally just stored in the ELF, and we are using this LEA addressing instruction to get a reference to this thing right here. So that's what's going on there. Cool. So now we've got the location of our array. Again, this array right here. Location to it, living right in RDI. And then we call max. I guess also one other thing to point out is that we put hex 20 into RSI. So I'm noticing this is a bug, right? This is the size of our array, at least what we meant by the size of our array. We don't have hex 20 many elements, right? We only had 8 elements. This is 8 times 4. And the issue is, I don't write enough C, size of is doing the actual size of this. Like how many bytes of memory does this whole thing occupy? If we want to write this correctly, what we really need to do, oops, not divide, I'm so used to Python // make sure we get an integer. Size of, can you do size of unsigned int? Is that valid syntax, or do I need to do size of A0? Let's see. Yeah, now we've got 8. So we've got 8 elements, so we're passing that into RSI. That's our second argument. That's what needs to be passed here, the size. And then we've got RDI set up, a pointer to that location. Remember, it's just a little bit past the instructions. 2E B5 past this instruction right here. So those bytes sitting sequentially in memory. And then we call max. So here is a first point, since we're trying to answer the question of what the heck, why LEA? Why do we have this complex addressing scheme possible? This is a very common thing to do. It's called RIP relative addressing. It's so common that this is very useful, that we're able to do RIP plus something. So this means it's this world of what's called position independent. We'll learn about this in later modules even further. But we've got this position independent addressing scheme, which for our purposes just means something relative to the instruction pointer. All we know is what we want to access is definitely going to be at this address where we're currently executing the next instruction. RIP is always pointing at the next instruction. Plus this small-ish offset, that's what we're talking about. We're not talking about specifically address hex 4077311200. We're talking about just a small offset away from our current instruction pointer. Okay. And now if we go into the max function, here is how the compiler decided to implement that. So we test ESI. So test, very similar to compare. In fact, if I pull this up, we can see what the difference is. So this is the compare instruction. This is the test instruction. So we can see compare to operands. Test, logical compare. They're both comparisons. And if we read this description here, it says for compare that it compares the first source operand with the second source operand and sets the status flags in the eFlags register according to the results. The comparison is performed by subtracting the second operand from the first operand and then setting the status flags in the same manner. So basically it determines what the relationship is between these two values by subtracting them. Okay. This computes the bitwise logical AND of the first operand, source 1 operand, and the second operand, source 2 operand, and sets the SF, ZF, and PF status flags according to the result. The result is then discarded. So in both of these cases, we're discarding the result. We're just effectively doing a sub instruction versus an and instruction and setting some flags. So this right here, so we can see right, we're setting the 0 flag. So if when we do this logical and, it is 0, then the 0 flag is set to 1. So that would mean that if you and two values together and it's 0, the 0 flag, that would mean that one of these arguments is definitely 0, right? So in our case, we're doing a test ESI. The only way that one of these arguments could be 0 is if both of them are 0, because they're the same thing. So that would be what sets the 0 flag. And then we also can set these other flags. Okay, we're not going to go too far into that right now, but that's what's going on. So then we do a jump if less than or equal to, which goes to 1154. So right here, which puts 0 into EDX. We're going to have to figure out what the heck EDX here is in a second. We don't really have the context of what's going on here. And then it jumps back up to 1151, which puts EDX into EAX and then ret. So I guess what's going on here is that if we make this jump, we're putting 0 in EDX, which means we're putting 0 in EAX and we're returning. So if RSI or ESI, so our second argument, if that is a 0, we return 0. So let's look at this. If this right here is 0, we return 0. This makes sense because we initialize to 0. If size is 0, we're not doing this at all for sure. And we're just returning what it initially was. So this is like a quick little escape, right? It decided that it wants a quick escape, that if we pass 0, get the heck out of here, just return the 0, which was our initial value. Otherwise, what's going to happen is we're going to take the first argument, RDI, so the pointer to our array, and we're going to put that into RAX. We're going to take RSI minus 1 and put that into EDX. So whatever our size is, minus 1 goes into EDX. And then we're going to do this complicated addressing scheme. We're going to do RDI, so whatever our first argument to our function was. So the base address of our array. Let me make sure, actually, that we're not in the square. We're going to take the first argument, RDI, the base of our array, and we're going to add RDX to that, times 4. So the size of an integer is 4 bytes. So it's going to be times 4 plus 4. So why this complicated thing? Well, it turns out, and we don't know yet why. We're going to figure out why the heck it decided to do this. Remember, as long as it's correct, the compiler can generate whatever assembly it wants to. It might not make sense to you. You might say, I wouldn't have written it like that. As long as it's correct, the compiler can generate it. So it decided to subtract 1, put that in here. And so this kind of, at least so far, this works on the first case for accessing it, right? Because we're looking at the base of this entire array plus the size minus 1 times 4, so almost all the way to the end, the second to last element, plus hex 4, which means to the last element, right? Let's make sure that's true. I might be off by 1, though. I think we're about to jump into GDB so that we don't have to guess here. Yeah, let's go ahead and jump into GDB so that we can demonstrate that things are correct as we go. Nice. Okay. GDB test_c. We're going to do -q. We're not going to be doing what we've been doing in class for, well, should we? Maybe we should. How do I run that like that? We'll do this. Okay. Wait, not dog. Test C. We're going to break at max, and we're going to continue. Okay, so what the heck has been passed in? Remember, RDI, or let's start with RSI. This one's a little simpler. Is 8. We've passed in a size of 8. It's got 8 elements to this array thing. 8 elements. We'll add some nuance. We're nowhere near the camera. 8 elements. Okay. And then what has gone into our DI? What's this address right here? What the heck is this address right here? Well, if we try to print this, let's say we print 8 bytes at this address right here, we see that we've got 01, 00, 00, 00, 00, 02, 00, 00, 00, 00. These are the little endian 32-bit integers, so we can print that as follows. If we wanted to see them, it would be no 8. Oh, that's right. Giant words would be if it was 32-bit integer or 64-bit integers. What is it? How do I print? Signed. Let's see here. Uint 32T. Does this work? No. Everyone's got to have a different naming scheme. For some reason, it's not enough to say it's a quad word. We got to have giant words. Now I got to remember what the heck thing that's smaller than a giant word is. Not good, GDB. Why would you do this? A giant word? Well, what the heck? This documentation is also terrible. Is it just like it says that the giant is 8 bytes? What the heck is 4 bytes? Is it a word? Are we calling a word this? Let's see. Oh, we are. Okay, wonderful. Why not suddenly? Someone says a word is 16 bits, someone else says a word is 32 bits. Fortunately, we don't get very good standards here. Okay, so we can see that this address right here is R1, R2, R3, R4, R5, R6, R7, R8. Okay. Cool. So we got those loaded up. We test ESI on the beginning. So let's step. We're about to do this test. And now we're about to jump. So we're expecting it not to jump because this is not 0, so we should not jump. We should fall through to right here, right? Because ESI, RSI, is not 0, it's 8. Okay, so we take RDI, we put that into RAX. So RDI, again, the base of our array, we put that into RAX. Okay. We take RSI minus 1 and we put that into RDX. So RDX is about to become RSI minus 1, RSI 8, minus 1, 7. So we're about to see 7 appear in RDX. Okay. 7 is now in RDX. And then what's going to happen next? We are going to do this complicated thing. So we're going to take RDI, the base of our array so far, at least, plus 7 times 4 plus 4. Let's see. What the heck is pointing in RSI? This is what we're trying to answer. It's a little bit of a complicated thing. Let's make sure we understand what is in here now. So we've got RSI loaded up. What is RSI pointing at? So before we printed out this whole array of things, we know it's somewhere either in or right next to this giant array of things. I'm thinking we're just past it. So if we print it as this, are we going to see 1, 2, 3, 4, 5, 6, 7, 8, or something else? Yeah, something else. We're actually just past it. So that's what we've decided to do. We've decided to put address just past it into RSI. Again, why are we doing that? We're about to find out. The compiler is free to generate whatever code it wants as long as it's correct. Then we put 0 into EDX. Okay. So that is no longer going to be this like 1 less than the size business. It's about to be 0. And then we've got our AX, which again is the base of it all. So that's going to be, we're going to pull out of memory a D word pointer, as in 32 bits. We're going to pull the first element out because currently REX is pointing at the first element. We're going to pull that out of memory, put it in ECX. So 0, EDX, first element, ECX, and we're going to compare EDX with ECX. So we're comparing 0 and whatever the first element is. Now, we've got ourselves another fun instruction, right? There's a lot of instructions in x86. We haven't yet seen this C move B instruction. C move B. Well, close enough. C move, and we got a whole bunch of different varieties. We got C move B. It's a conditional move. What does it do? Each of the CMove instructions performs a move operation if the status flags in the eFlags register, blah, 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 are in a specified state or condition. A condition code CC is associated with each instruction to indicate the condition being tested for. Okay. So we're conditionally moving. Move if below. So that's what this means. The B means below. Move if below. As in, if EDX is less than ECX, if EDX is less than ECX, move ECX into EDX. This does what we expect, right? This is implementing this right here. All three of these lines, or 2 lines, 3 lines, whatever you want to call this, is doing this all in 2 instructions. So it's actually not doing like a branch or something. It's not doing a jump. Instead, it's just conditionally moving it. And this makes sense, right? If our current max value, which we start out with a current max value of 0, if our current max value is less than the very first element, presumably we're going to start looking at other elements soon, but at least the very first element, if the very first element is or if the current maximum is less than the very first element, put the very first element in as the new max, right? We're assuming that this EDX thing is holding our max. And then what? Then we add 4 to REX. So now we're going to move the pointer forward by 4. And we're going to compare REX with RSI. So this is why we did this crazy RSI thing. RSI we set up for ourselves the very end, just past our array. So now we're tracking where the end of this array is. And so if we're at the end of the array, we jump to max plus 24. So this 141 address, 141, or max plus 24 right here. If it's not equal to, then we go back and we do this looping thing. So we just keep executing this until it is equal to the end. So we're adding 4. So every time we're adding 4 to REX, we're getting closer and closer to where it is going to be equal to the end, at which point, what do? We take EDX, which as we said before, is our maximum value. We put it into EAX, we return. So maybe this isn't how you would write this assembly, now that you've got some experience with assembly, but this certainly is a way to write this assembly. And it looks like it's pretty optimal here, pretty efficient. And I mean, I'm saying that just because I'm not seeing a whole bunch of extraneous instructions. Compiler research is a whole field. People do lots of very intensive measurements on benchmarks to see which instructions run faster under which circumstances. There's a lot of thought that's gone into the emitted code here, following a lot of heuristics. Okay, so let's watch this happen. So really all we care about is this EDX thing. EDX thing holds our current maximum. So we step, our current maximum RDX is 0. if we set up a breakpoint here, because remember, every time we break, we're going to here. So let's break at this address. So currently RDX is 0. We would expect that this is just going to increment up every pass through this loop because we're walking through this array and those are each sequentially getting larger. So we're expecting that if I continue, RDX should become 1. Sure enough, it's 1, then it's 2, then it's 3, then it's 4. Also, we can see that RCX is going up each time. Well, that RCX is whatever the heck we just pulled out of here, right, in the last loop, so that makes sense. 5, 6, 7, and well, I continued all the way through, but it became 8, and my breakpoint was slightly off. And so this code works. Hopefully that makes sense. It's a little confusing. A lot of this is experiential. Reading assembly, getting very familiar with it. That's what's going on here. Okay, so so I'm seeing a question. Hopefully that makes sense. If there's any questions, feel free to ask about that. Again, if you're like, this is a mess, this seems like a disaster, this really is an experiential thing. Like you get used to looking at assembly. This is the whole purpose of many of these modules, unfortunately. If you're scared of assembly, have to do with assembly. You're going to be reading a lot of assembly in this class. And hopefully with each challenge you solve, you get a little more comfortable with it. You might hate it still all the way through, but you're going to get more and more comfortable with it. And things will start to make more sense. Okay. Having issues understanding how we can set all the bits except the least significant bit to 0 without using a mask, such as 0, 0, 0, 1. Okay, so you're talking about how can we set all the bits except the least significant bit to 0 without using a mask such as this? So this is a good question. So you're saying, for example, if we have some value, and let's say that it is 0, 1, 0, 1, 0, 1, 0, 1, 0, for example, and we have our mask, which is this. If we AND these two things together, so we'll say, I don't know, AND, we would get all zeros because this mask is just looking at this last bit. Everything gets turned to a 0 because the mask says all these things are 0, except we get to keep whatever the heck this last bit is. So if instead we had a 1 here, this would become a 1. And really, none of these bits here matter because they're getting ANDed with zeros. So I'm curious if you're actually interested in bits or bytes here. I've got a feeling you're actually talking about bytes and not bits. Which we could do this same sort of idea here with bytes or bits, right? I mean, basically what I mean by that is, so how many did I do? Did I do 8, 4, 5, 6, 7, 8? Yeah, so this is 1 byte. If let's just make this maybe a little bit clearer to read by turning this into 2 bytes, right? And so if we wanted to just keep the least significant byte, we would have a mask like this, right? So we'd have this byte, or this is all zeros, this is all ones, and it together, and we keep this, right? So we're just keeping the least significant byte in this case. And if we, do this as our value, and we take this mask, again, the least significant byte, not bit, but byte, just means 8 ones in a row, we would have this as the result, right? This is the same idea, it's just extending out from 1 bit to 8 bits. And presumably these are all ones or all zeros because we're trying to keep the least significant byte. At least I think that's what you're really talking about. You said LSB, but you're talking about bits. Pretty sure you're talking about bytes though. If we wanted to do this without this AND operation, in the case of a least significant byte, if we say that value is, for example, RAX, right? We currently have, well, we'll say the value is this, and we'll, how to express this? We'll say that this is in RAX. Maybe we'll do that. And maybe our mask is in RBX. ANDed together. So we're just putting some names on these things because maybe you have this value put into RAX, you have this mask put into RBX, and then what you do is you do AND RAX RBX, and suddenly, we'll make the spacing here makes sense, and we'll copy ourselves here. Hold on. Text editors only go so far for visualization quickly. This. Okay. So you do this instruction right here, and RAX with RBX, and you get the result you want. You keep the least significant byte, but everything else just got screwed. And maybe, I'm saying RAX, there's a whole bunch of extra zeros at the beginning of all of this. We're only looking at the least 2 significant bytes of RAX. So in other words, move 1, 2, 3, 4, RAX, move RBX 0x 00FF, and then and RAX RBX, right? And now we just keep the least significant byte. This hex 34 would be the result. And you're saying, how do I do it without doing this and? So specifically, if we're dealing with bytes at a time, we can abuse the fact that we have smaller registers. So this is a question of investigating a single register at a time. Well, okay, there's a number of ways to do this. So it's kind of depends on your constraints or what you're trying to do here. One way to do this, to just pull this least significant byte out of RAX, would be to move into, let's say, some other register 0. So we just zero out RCX. That's all we're doing here. We're making sure RCX is 0. We're making that very explicit. And then instead of doing an and, another way of expressing this, just because of what this particular flag was, we don't even need this, but just because of what we mean, just a single byte, what you can do is you can do move AL CL, or got that backwards, CL AL, and then, well, move RAX 0, move AL CL, right? And what we're doing here with this is we're just taking the least significant byte, because that's what this means when we register a part of the register. We're pulling this part of the register out. We're putting that into CL. So CL is definitely just the least significant byte now of RAX. And we want to make sure that that ends up back in RAX, because technically that's what this does. Zero out RAX and move CL back into AL. Or in this case, you could even do RCX, RAX, because we know that the rest of the bytes are 0. This would also work just fine. So by using parts of the register, the least significant byte of the register, which is what CL and AL refer to, you can just do kind of the equivalent of this AND thing by pulling just a single byte out. Hopefully that answers your question. I will say there's another approach to this. There's probably several approaches to this. You could do, let's see here. Can you do LEA? I'm trying to think. Can you do like LEA, RAX, AL? Is that? Can you do it that way? Because basically the issue is you can't do move rex al because this is an 8-byte value, or a single byte value, and this is an 8-byte value. And if you do a move, they need to be the same size. You might actually be able to get away with doing this with LEA. Let's see. Does this assemble? Move rex hex 1, 2, 3, 4. LEA. Oh, the issue though. No, that. Let's see. Make. Ooh, it's not thrilled about that one. It's not a valid. Yeah, I'm guessing we can't do that because I think this would make. Yeah, that would make just fine. I guess you can't. You could imagine the architecture supporting this. It does not support this though. I wonder if you can do. You can probably do EAX, right? EAX is just fine. Maybe even do AX. No AX, no AL. You can't do that. That path does not work, but you could imagine an architecture that work. It just happens to be that you can't do that here. But there is another way that comes to my mind. You could take, so for example, let's say we initialize with 1, 2, 3, 4. There's another instruction that we haven't talked about here, but I believe the challenges talk about this instruction. It's called the shift left instruction. So this is another bitwise operation. In the same way that and is a bitwise operation or is a bitwise operation, there's shift left, which literally is like shifting the bits left and right. There's also a corresponding shift right. So you can shift bytes right, shift bytes left. And what happens is if you do, like, for example, shift right rex 64, you're just shifting all 64 bits of rex to the right, which means like past where rex exists, like it's deleting them effectively. So this would zero out rex. Similarly, this would zero out rex. So you just shift all the bits to the left. If you wanted to grab just the least significant byte, you could actually, let me think about the math here. I think what you could do is you could shift this left 8 bytes less, so 56 bits. So what this would result in is that rex would currently be equal to 0x34, 1, 2, 1, 2, 3, and then 1, 2, 3, 4. Right? So initially, it would have been this. You shift left rex 56. Say rex equals this. You shift it left 56. All of this, like this would be 8 bits. This would be 16 bits, right? Hopefully it's right clear. And as you go all the way up to 56 bits, these 1, 2 falls off, and now you've got this. So that would do that. And then you could shift right rex 56. And now rex would, all these 3 4s, right? Initially it was up here. Well, this would be 8 bits shifted right, 16, 24, 32, and so on, all the way back to 56. So this like effectively just deleted these bits. So this would also do it. Hopefully that answers your question. There's a number of ways to do it. It just depends on your constraints, if you have constraints for this, which I'm guessing, right, you're talking about the challenge. I don't know what the constraints are on your challenge. Don't remember. But this is a number of ways you could do the same thing. There's all sorts of ways to do the same thing in assembly because I mean, we get full power of like logic and stuff that, you know, just got lots of routes to doing this. All right, I am going to wrap up my office hours here. Hopefully it was useful. I guess I'm seeing, I don't think I addressed this. The address mentioned in assembly, isn't it the virtual address generated by CPU or physical address, address of page mapped to the memory? So for our purposes, I guess I'll point out to this. I know this was a while ago, but I will say it doesn't matter for our purposes. So we are talking technically about virtual addresses, but that's just because we're in like Linux and technically the CPU is in virtual, it's doing virtual addressing stuff, you technically could write a bootloader, and this code could be running against actual physical memory. It doesn't really matter for our purposes. All that matters is that we have some sort of thing called memory, and it's just a bunch of sequential bytes in a row. Whether this is technically virtual or physical doesn't matter. We don't care about that concept. But technically, we are using virtual addresses. One last question for online students. How do we attend recitation? That's a good question. So for the online section, I mean, you have the option, I guess, if you're in the Tempe area and you are interested in attending recitation in person, you're more than welcome to do so. Of course, I'm sure there's a number of online students who are not in the Tempe area / are unavailable for doing that. In which case, unfortunately, I mean, we don't have a physical location for you to go to if you can't physically go to a location. So ask your questions here during office hours. Every week I'll be doing this office hours. And ask lots of questions on the Discord. People are constantly helping each other on the Discord. Effectively, the Discord is just one never-ending recitation. So ask your questions there. Okay. Thank you all for attending, and good luck with the module. Remember, it's due very soon, and do it before the last day. Otherwise, you're going to be potentially miserable saying, wow, this computer is the server is so slow, it's so miserable. Just save yourself the headache and do it early. All right, goodbye.